It's time for cross-validation, a new topic. Let's start with testing machine learning models. Testing a machine learning model on the training set is problematic. Strong models like decision trees easily overfit the data. Although scores may be perfect, models that overfit generalize poorly to new data. Predictions of new data are bad, simply put. Okay, it's important to understand this. So the idea is something like this. A machine learning model is only as good as it's going to perform on new data. In the real world, machine learning models are built, and then their performance is on new data, new scenarios coming in. So when building a machine learning model, it's critical to see how it's going to do on new data. Overfitting doesn't generalize well because it's too biased toward the data that you have. You want it to be strong for all data, not just on the data that you happen to be training it on. And we saw that in particular with decision trees when scores went from like 1.0 to 0.6. Okay? Splitting the data into a training and a test set is better. However, different test sets can lead to different scores even though the model is the same. The idea here is as follows. If you have a test set and the data points are really problematic and challenging, well, the machine learning model is not going to give you a good score. Does that mean it's bad? Not necessarily. It might be that the data points are challenging. Possibly another test set would reveal a good score, and a more representative test set would reveal a more balanced score. So there is an issue here with the test set. And these in general are the issues faced when testing a machine learning model. Okay? So, cross-validation to the rescue. The solution is cross-validation. Cross-validation splits the data multiple times into training and test sets. The key here is multiple. Okay, not just once, which train test split did. It's going to do it several times. For each split, a new score is generated. So it's kind of like this. You split the data once, then you go back and do it again. You go back and do it again. You reset it and get new scores each time on new test sets and on new training sets. The average score of all splits is a better indicator of how well the model performs. Okay, let's take a look at cross-validation more in depth with a nice image. So, here we have a cross-validation image. If you look at iteration number 1, consider that all the data. You have a row of, say, red and green. And, these are the results, say. Like, each row has a red or a green result. When I say result, it's like the target column, okay? All the data is trying to predict, is it red or is it green? So iteration number 1 suggests, hey, on the right side, this is our training set, and on the left side, that's our test set. So you train it on all the marbles on the right. Well, they look like marbles to me. And then you test it on the ones on the left. That is one standard train test split, okay? However, with cross-validation, you do it again. And the way you do it is you shift the test data. So if you shift it, and you set aside now this middle group, then the rest of it becomes the training data. And you train on the new data and test on the new test set. So you do it again and you get a second test score. Similarly, with the third iteration, you go back, you do a new training set on the model and a new test set, and you get a third score. Then it goes down to iteration K, indicating that you could do this as many times as you want. The norm is 5. Sometimes you see 3 and 10, and others as well. Okay, so that's cross-validation. In effect, it is train test split multiple times to get multiple scores to get a better indicator of how well the model performs on unseen data, which is its true test. Okay, now let's look at cross-validation in terms of code. So from sklearn.model selection, import cross-val score. It's like what we've seen before. Now, what you do is I assign cross-val score to a variable called scores because it's going to produce multiple scores. And what you need inside of cross-val score is your machine learning model could be whatever you want, and your X, right, which are the columns that you're using to make your predictions, and Y, which is the column that you're trying to predict. Now, the beauty of this is that you don't need to kind of initialize the model or fit the model. It fits the model for you. So it fits and scores the model for each round. Okay? Crossval score by default will give you 5 scores. What I like to do then is take the mean, which you can get using scores.mean, to get the average of them all. Okay? It's kind of simple and elegant. Now let's look at some default parameters. So CV equals 5. I don't usually change that. That's the number of splits. Like, you could do it 3 times, you could do it 10 times. It kind of depends on your data. If you had like a really small data set, 5 might be big, you know. If you have an enormous data set, maybe you want to go higher. Another is the scoring. So we haven't talked about scoring metrics yet, but we will soon. And by default, the scoring is accuracy when? Well, when it's a classifier, when your model's a classifier. You could also have negative mean squared error, which is actually the norm for regression. We have not discussed this yet. I'm simply highlighting that in regression, you can also specify the scoring mean right here. And we will, the scoring parameter. And we'll talk about scoring metrics in more depth in a later lesson. So just going back, here's the cross-validation code. It's nice and clean. You import it, you score it, and then it's usually helpful to take the mean, because when you have 5 decimal places, it might have like 8 decimal places, it can actually be hard to distinguish which one is better when you're looking at 5 all at once. Scores.mean will clearly reveal it to you. That's cross-validation code. I use it a lot. You should too. Happy coding. Let's do it in Colab.